by not asking you for your consent. Hey, all right, we're starting the record now. Let's go ahead and start off with this warm-up. Hopefully you had some time to try these two problems. If not, I suggest you pause this video and write these down and try these first before you watch this and see if you can get this. Now, looking at some of the people who have already participated in the pair deck, right, you saw that there's no rules here that allows us to integrate 3x squared times the square root of x cubed plus 1 easily, right? I can't split those functions up and then just do one without the other, separated from the other, right? I can do the integral of 3x squared pretty darn well, but since it's multiplying with the square root, it doesn't work out as easy. So the first technique that we've learned is to see if we can use U-substitution, right? Does U-substitution apply here? And in order to use this technique, the first thing we're observing for is to see if one function looks like it's the derivative of the other function. Now there's like multiple functions we can group things as, but one that's going to help us is if we group this function right here outside and then just only look at this function inside right here. I'm not going to include the square root part of it just yet. Looking at this, I see that the 3x squared is a factor of a derivative of x cubed plus 1, right? So since that is a derivative of that, I'm going to go ahead and use U-substitution. So for U-substitution, we go in there and we let u equal to the non-derivative form, right? Not the 3x squared, that is the derivative. I'm going to let u equal to the non-derivative form, which is the x cubed plus 1, right? And if you don't get this concept yet, right, try letting u equal to 3x squared, and you'll see that you kind of get stuck, right? You kind of see that you'll get stuck, because if I do it this way, right, and I hit here du is equal to 3x squared dx, right? That's the second step, right? I'm sorry, that's the third step, is to get the du, get this differential by taking the derivative of both sides, and solving for dx. So I'm going to go ahead and divide by 3x squared. I end up with du over 3x squared. This is equal to dx. Now, here's the thing. What I'm trying to say is when you do this, right, what I'm hoping you will notice is when I replace the dx with this into here, and I replace the x cubed plus 1 into here, right, you end up with this problem right here. We'll end up with the integral of 3x squared times the square root of u times, instead of dx, it's du over 3x squared. Now, when I work out this problem, the 3x squares cancel out. See that? They cancel out. And I'm going to be left with the integral of u to the 1/2 du. If I had done it the other way and I let u equal to, right, this is a hypothetical, if u had equal to 3x squared instead, and I take the derivative here, I would have gotten du is equal to 6x dx, which means that du over 6x is equal to dx. If I tried substituting with that, right, I would have ended up with the integral of 3, instead of 3x squared, right, it'd be the integral of u, which, hey, knocking, that doesn't look so bad so far, but check this out, as the square root of x cubed plus 1, and inside here the dx would be du over 6x. And the problem with this is I can't cancel out this x with this x. That x cubed is inside a radical, and it doesn't cancel out as easy because of that radical, right? Algebraically speaking, you can't just take a variable and cancel it into another variable that's hidden inside a radical, a sine function, a cosine function, or any other functions, right? It kind of messes it up. Right? I can't just cancel it out. So since it doesn't cancel out, I don't know how to integrate this, right? That's just a mess. So that's why this one didn't work out. So again, don't fret if you tried U-substitution and it didn't work out. Try letting u equal to something else and see if that helps with the problem. And if it doesn't, then you might not be in Calc AB anymore. You might be in Calc BC, where U-substitution, does have its limits. Its limits. Actually, it happens in AB as well. It does have its limits here, but I'm going to show you that later. All right, let's go ahead and finish off this problem. The integral of u to the 1/2. That's just the power rule, right? Power rule here is going to be u to the 1/2 plus 1, which is going to be 3/2, right? Divided by 3/2, which is going to be reciprocal to 2 over 3 plus c. Right? That's the power rule in a nutshell. And your power can be any number. It could be a fraction. It could be anything except 0 or -1, right? That's for the power rule. All right, you're almost done. You did the integral correctly. Now that's all that's left is to substitute back the original u, and in this case, u was equal to x cubed plus 1. So we have here 2 over 3, and inside here we're going to replace it with x cubed plus 1, right? Close that off. This is to 3 halves plus c, and that's your answer. That's us integrating it, and that is done. Right? That's not too bad. That's not too bad. Hopefully you don't think it's too bad. All right. With that being said, let's keep going. Let's move over here. Number two I thought was interesting when I was looking at your work. Oh, look, we have so much more people here who clicked in here and put their names on there for the first one. The same thing for the second one for me so I can see it. Now there's 6 of you in here. That's awesome. And that you showed what you think u should equal to. At least that. That's not bad. So right off the bat, looks like most of you attempted to do U-substitution here as well, right? So you looked at this and you're like, 2x does look like it's a factor of x squared. So U-substitution can be done, right? So you can go in here and you let u equal to the non-derivative, which would be not the 2x this time, it would be the x squared, right? X squared plus 1, right? I'm including the plus 1 because when you do the derivative of plus 1, it just goes to 0. And I can kind of see that there's no worries there, right? It will just be easier to deal with. So when I do this one, I had du is equal to 2x dx. And that means that du over 2x is going to equal to dx, right? So I got what dx is equal to. I have what u is equal to, and I'm going to go in there and substitute out some stuff here. So this is going to become the integral of 2x times u times dx. dx, of course, being du over 2x. The 2x's cancel out. I end up with the integral of u du. Man, it's so much easier to deal with now. The integral of u du is just going to be u to the second power divided by 2 plus c. Replace out that u with what u was equal to originally, which is going to be, I'll put the 1/2 in front here. The u is x squared plus 1, right? Squared plus c, and you're done. And you're done. Now, you ready for the trippy part? You could have done this problem without any U-substitution. U-substitution is a nice technique, but it's not always necessary. It's not always necessary. It is not always necessary because one thing you could do is, for example, if you take a look at this one right here, if I have here the integral, what if I just simplified this? This is not a square root problem. Can't I just distribute this? If I distribute this, what do I get, by the way? What do I get? Any clues? Any ideas? 2x times x squared, that's going to give me 2x cubed. Yeah, plus 2x. Quantity, of course, this whole thing is being multiplied by dx. Isn't there a addition property that we have in integration, right? If there's no crazy things like this, can I just split this up into 2 integrals? This is the integral of 2x cubed dx plus the integral of 2x dx. Isn't this not that bad? If I could go ahead and integrate this, I should get, did I do that right? I think I did that right. I should get over here, this is going to be x to the 4th, right? Times over 4, this of course being multiplied by 2, plus, right here, that's going to give me x squared plus c. Huh. Which then if I simplify this out, this will be 1/2 x to the 4th plus x squared plus c. That doesn't look like the answer we got when we did U-substitution. In theory, we should have got the same thing. Did I do something wrong? What do you guys think? Did I make a mistake somewhere? Or are they actually equal to each other? Let me know. What do you guys think? I want to know right now. What do you guys think? Is there something that I did wrong somewhere? Or should I or what should I do to check to see if they are equal to each other? What could I do? Any ideas? Is there a way for me to check if this over here is the same thing as this over here? Differentiate the solutions? Yeah. We could take the derivative and see if we end up back at the original problem, right? That's one thing we could do. Take the derivative of the left side, see if we end up back at the original problem. Take the derivative of the right side, see if it ends up with this problem, which hopefully we distributed correctly, right? That's one thing we could do. That's awesome, Monica. Good job. All right, we can go in there and check that. Another thing we could do also is simplify this one on the left to see if it does look like it's simplify the first one. That's right. Choose a point. You could do that too, Brian, but that's going to actually, we can't choose a point. Actually, we could choose a point. But then how many points would we need to choose to? So that's a good starting point, though. We could choose a point to see if they equal the same amount when we plug it in, right? Those are all valid answers, by the way, Brian. That's good. Monica, that's good. Those two solutions would work as well. We can simplify the one on the left, right? We can FOIL this out. This will be 1/2 x squared. Nope, knock me. If you FOIL this, it would be x to the 4th plus doop boop. That's me. X squared plus x squared will be 2x squared plus 1 plus c. When you distribute the 1/2, this becomes 1/2 x to the 4th plus x squared plus 1/2 plus c. Oh, this is where things get a little interesting to me. That doesn't look perfect, does it? But why is that? 1/2 plus c. Do you know what that is? It's a constant plus a constant. Do you know what a constant plus a constant is equal to? Constant plus a constant. That's just equal to c. Yeah. That's weird, isn't it? That's weird. Oh, by the way, there's no right answer for this one. Which one's the most correct way of doing this to check to see which one's the right method or not? Welcome to integers. You got different methods, you got different techniques, and sometimes they'll lead you to two different looking answers, but both are right. They're just right in different ways. Okay, which one's the correct way of doing this problem? Whichever way you're comfortable with, as long as you're doing the correct steps. U-Substitution is a perfectly fine method. Simplifying it and using the rules of addition for integration, perfectly fine method as well. It's just up to you, whichever one is the easiest. And I think that's going to be the hardest part and the biggest hang up for most calc students. It's just, how do you start a problem and which way is the most correct way? And I'm just going to let you guys know right now, don't get hung up on that. That can like cause a lot of stress of like saying, well, what if this is not the easiest way? No one cares. Just do it the right way. And you'll say, well, now you're going to stress out which one is the right way. And that's the correct thing to stress over. Is this the correct way of doing it? You just try. Make sure that you follow your rules and you follow the rules of math, and then you should be fine. Don't stress out over this one too much. All right? Okay. With that being said, let's go ahead and let's take a look at some other problems here. Let's take a look at another example. I'm going to give you a blank screen for you guys to try this one. And again, I'm checking your attempts here in class today. So I'm actually asking you to fill out on Pear Deck your responses on here. So if you notice, there's a blank screen on the third one. I'm going to be forcing you onto that one right now. I want to see you guys try this one right here. You ready? Let's take a look at this one right here. Let's say I have the integral of secant squared x times tangent x plus 3 dx. So what should we do to start this one? And I don't know. I don't honestly have the answer for this one. I'm just looking up random questions right now just for us to practice. I'm going to go ahead and force you guys on Pear Deck into a blank screen. And my mouse isn't working. Where are you, mouse? Oh, you're over here. I'm going to go ahead and force you guys all to the third screen here. And you don't have to copy down the problem, but if you want to copy down the problem, you can. What should we do here? Should we try what we did with number 2 on the last one? Should we try distributing this? But then distributing this, I'm going to have a secant squared tangent plus 3 secant squared. That's not actually going to help me too much, is there? Because that's going to be a lot of secants. And then there's going to be secants times stuff, and it doesn't work. Can you use U-substitution? Yeah, I would try U-substitution. Let's go with that, Max. I like that. So I want you guys to try it right now. What would you let U equal to? What would you let U equal to? And some of you are going to see this faster than others, and that's going to be perfectly okay, right? Don't worry if you don't see it right away, but if you want a hint, you're looking for patterns in a sense that you're looking for, is there a function, if I were to take the derivative of it, looks like the other function? It looks like some of you guys already see it, and Brian's already typing into the chat. Brian V's already starting it out. Some of you guys might know already. The derivative of tangent is something you already know. Now, here's my question. Do you just let it equal to just tangent, or do you let it equal to tangent plus 3? Is one more right than the other? Will it still work? Try it out. Work it out. I want to see it right now. Brian B, looking good so far. Keep going. Angela, good start for letting U equal to tangent. Keep going. Keep going. Leslie's going with tangent x plus 3. I like it. I like it. Oh, Michael, you're ready. You're about at the right step to substitute in. That's looking good. Brian N is in there as well. That's an interesting 3, Brian. I like it. Emily, good on the tan x plus 3. Now you just need the du. Keep going. Look it up if you need to. What's the derivative of tangent? Good stuff. Rahish, good stuff. Fatima's writing it out. Beautifully written. Jocelyn, good. And Max, good on that letting U equal to that. Ooh. Sorry, I don't mean to keep yawning in front of you guys, but I feel sleepy. Drinking water, but it's not like waking me up. I think I need to like snack on something. Let's see if I have snacks here. Let me look around real quick. Oh. I have Pringles that I don't know how old they are. Let's see here. Best by October 14th, 2021. These are still good. They should be fine. All right. So it looks like we're in agreement. Agreement? Agreement? Agreement. That in this problem, we're going to let U equal to tangent x plus 3. Now, if you really want some tips on this stuff, if you're going to let U equal to something inside a function, traditionally let it equal to the whole thing. Just because if you only let it equal to a part of it, you'll get this thing that looks like U plus 3, which isn't that bad to integrate, but sometimes it could be annoying to integrate. Like you have U plus 3 and then it's being multiplied or taking the square root of it. You can't use the power rule, right? If I had the square root of U plus 3, right, that's not something I can easily integrate. I can't use the power rule for this because the power rule only works if it's a single thing raised to a power. If it has that plus 3 in there, it gets kind of like, it's not terrible, but it's just annoying. So traditionally, we try to let U equal to the entire thing. Sometimes, though, it's better to let U equal to a part of it. And how do you know which one is which? Like I said, it comes by a problem basis. Like we don't know which one is the best way. You just have to go in there and you just try it. I know that sounds like, thanks for not giving me an answer, but this is how it is. Now, this step right here. After you let U equal to this, you have to find the derivative of this by taking the derivative of both sides. Derivative of u gets you this differential. Du is equal to secant squared x dx. Derivative of 3 is just 0. Don't forget the x in there, right? Don't forget the x in there. So du over secant squared x is equal to dx. I like color coding my stuff. I can see that u is going to be replacing this right here, and dx is going to be replaced by du over secant squared. So that's step 3, right? Step 1, 2, and 3 in a nutshell is getting this part right here. Step 4, we just substitute in and simplify and see if it actually comes out to something that's easy to deal with. So I have here the integral of secant squared x times tangent x plus 3 is just going to be u. You see how much easier that is to deal with, to write? I know, like I said, the plus 3 doesn't seem like it's a big deal, but you know, sometimes it's just a little bit nicer. And then we have here du over secant squared x. The secant squared x's cancel each other out. The x's don't cancel each other out. The secant squared x's cancel each other out. Make sure you understand the difference between the two. Okay? I end up here now with the integral of u du. It's trippy, yeah? U-substitution is a nice way to, if it works out, it turns into a very nice problem, doesn't it? Because the integral of u du, that's just the power rule. I end up with u squared plus u squared over 2 plus c. U squared plus c. There's nothing else. Is there anything else there? I don't think so, right? I simplified the u and the du. Have I made any mistakes anywhere here? Please let me know. Please let me know. And then finish this off, replacing the u with tangent x plus 3. This, of course, is being squared divided by 2 plus c. And that should be my answer. That should be my answer. I'm good? Awesome. Thank you, Monica, for double checking with me. But yeah, there you go. There you go. All right. Give you guys a second to copy that down in your notes. Now, I think I gave you homework on U-substitution already in the book. You might want to have some practice on there, so you should start looking at these homework problems. Slope fields was a different thing, right? It kind of led us into this. That plus c is the idea that we can, you know, cover all our bases. And then finding a general solution, that's our general solution, by the way. Then finding our particular solution, they give us an x value and a y value. Now that just becomes a plug and chug. You plug in your x, you plug in your y, and you get what you should have as it, what it should equal to, right? Give me a second here. All right, so that cheat sheet right here, but I don't want to, you can look this up. You can Google these cheat sheets and you can get them yourselves. But I wanted to give you a little bit of notes with them as well. So I want to upload this somewhere, but I mean, I'm saying you could just Google this right here, especially these formulas right here. They also have the derivatives on the left-hand side right there as this cheat sheet, but I'm going to go ahead and just copy and paste this right here. And I'm going to have you guys mark a couple things here. So you guys see this okay? Is that all right? Right. So the integral of 1 dx, or just the integral of dx by itself, you could write it like that as well. The integral of dx is just equal to x plus c. Well, that's like, well, duh, right? Because the derivative of x is just 1, right? So that's on there. And then even the constant rule is on there. Derivative of a dx is ax plus c, but that's because you can move the a out in the front, right? And then dx, right? That's why it becomes that right there. So you don't need to memorize those, but it's just one of those things that you're going to be doing it so often that it's going to come second nature to you. Power rule you do need to know, right? That's this one right here. And you've been practicing that. We've done a couple power rules already, and we got that one right there. And power rule's cousin is if the power of that x is equal to -1, right? We end up with ln of the absolute value of x. Did I talk to you guys about that integral yet? I kind of always breeze over this, and I make that mistake every year. the integral of 1 over x is ln of x, but I always forget to tell this. You need to put absolute values around it. Natural log doesn't work when your x is negative, and it's a possibility that when you're doing this integral, that x value could come out as negative and still hold true. You just have to make sure you put the absolute value over that x, or else the function breaks. This is not the time to be eating. We're trying to talk. Put that away. Okay. Sorry. It was rude to me. Now, these 6 trig functions right here are the ones I've shown in the past. Like, they put them in, oh, this is bad. I don't like the parentheses there. But these are the ones that you kind of just like have to know like the back of your hand. The integral of sine is negative cosine, right? Because the integral of sine is negative cosine because the derivative of negative cosine will give you sine. So these ones are like the easy ones that you should know, because you should know the derivatives of these functions over here. This is where I was hesitant to like show you this, but I keep seeing these problems show up, and I'm a little worried that they might show up on the AP exam. These 3 right here, I lied. These 4 right here. The integral of tangent, the integral of well, I guess this is the one that showed up the most, the integral of tangent, right? It's like these other formulas. It's kind of just known. Once you see this, you don't have to prove that the integral of tangent dx is equal to ln of secant of x. You can just use that fact. Now, I don't like that, but it is one that you can just know that that's what it is equal to. I don't know if it's going to show up on your AP exam or not. So you can make a flashcard to include it, but it's not that strong of a deal. It's not that big of a deal if you don't know it. Okay. Another thing, this one right here, the integral of ln of x. This is a BC topic, so you don't have to worry about this unless you're going to be taking BC next year with me, or you're going to be taking Calc 2 next year or in the future. But just for the exam, you can just put this on hold and just worry about learning that later. You do need to know the e function ones. You do need to know the base a, the exponential function one as well. This is one that you do need to know. This one's an oddball, and this one is a little strange, but you kind of know it from the derivative. If you remember the derivative function, derivative of an exponential function, that needs to be on there as well. And then, like I said in the past, we don't need to know all inverse trig functions and their integrals. You only need to focus on these 3. Inverse sine, inverse tangent, inverse secant, or arcsine, arctangent, and arcsecant. And you'll say, knock me, they have it over here as well. And over here, it's a little bit different. It's just in case if that a is not 1. If the a is another perfect square, it works out the same way, but you just have to add a little bit more stuff. Like, for example, if this right here were, let's say, 9, then that would be 3 squared. So the answer would be arcsine of x over 3. And that would get you this answer, by the way. With tangent and secant, it's a little bit different. You have to make sure you include that 1 over a in front. But yeah, get these down. I will post. I mean, this will be on my OneNote, so you guys can refer back to this. But I honestly suggest that you make like a cheat sheet somewhere and have these down until you have them memorized, right? Because you're gonna have to know these basic ones. Now, if they don't show up, if your integral problems don't have something that show up on this cheat sheet, that means that you're probably gonna need to use U-Substitution or something like U-Substitution to try to figure it out. So let's take a look at some more problems. That's that's just how we get through this stuff, right? So let's try another one. Were you guys able to? Actually, you guys can just open up OneNote and get this yourself. Screenshot it, save it somewhere, write it down. Oh, I forgot to mention number 24 here. Excuse me. That's just, I mean, you can memorize that, but honestly, I wouldn't bother memorizing this one. I wouldn't bother memorizing that one. I mean, it wouldn't hurt to memorize it, but it's not necessary. All right, let's go ahead and try another problem here. Let's go. If you want to see that picture, like I said, it's on OneNote. You can open it up anytime, and you can see it. Let's try another problem here. Let's go with What's a good one? I feel like that's not as one that I would like, but you know what? Let's try it. Yeah, let's try it. Let's see what we get here. Let's go with the integral of 6x minus 2 over 3x squared minus 2x dx. Yeah, let's go with that. You don't need to put this on the pair deck. This is just one I want you guys to take a look at here with me, right? Hopefully you have trained your eyes now to see patterns, and you're hopefully able to see that one of these definitely looks like the derivative of the other, right? There's two functions on here. One function is being divided by another, and hopefully you guys can see clearly that 6x looks like it's a factor of a derivative of 3x squared, which I think it's a perfect match of it. So I'm going to go ahead and try U-substitution because, like I said, there's no quotient rule for integrals, right? So I'm going to go ahead and let u equal to the non-derivative, which in this case is 3x squared minus 2x. 3x squared minus 2x. Okay? Next step, find du. So du is going to equal to 6x minus 2 dx, of course. Integrate, solve for the dx. Isolate the dx, get it by itself. I end up with du is equal to 6x minus 2 is equal to dx. And go ahead and start substituting out, right? Dx is going to be replaced by that. And du is going to be replaced by that. So if I write this out, I should end up here with the integral of 6x minus 2 over u, so that's what I'm replacing that with, times dx, which in this case is du over 6x minus 2. Right? These guys work out because the 6x minus 2 cancel each other out. I'm ending up with the integral of du over u. Now, that's not too bad, right? What is the integral of du over u? Do we have that on our cheat sheet? I don't actually have a du over u in there, but Monica's saying that it's ln of u. ln of u. But is that okay, Monica? It doesn't look like this one. This one is the integral of 1 over x dx. I have here the integral of du over u. Is that okay? Are they the same thing? Is this the same thing as the integral of 1 over u du? And it is. It is, yeah. And that's why this does become ln of, by the way, don't forget the absolute value part. I kind of breezed over that. Yeah, it's the same, just a different variable. That's the first thing that you need to notice, that x and u are interchangeable with those rules that are on that page. Second thing that you need to understand is that this right here is equivalent to this. It's just written in a different way. And that's what people don't understand when they see fractions, right? They kind of realize or they don't realize that they are the same. And they are in this case. So I think that's the point I wanted to make sure that you can kind of see. Sometimes you need to rewrite certain functions so that they follow these rules right here that I'm asking you to memorize, right? Anyways, u is equal to 3x squared minus 2x, so I can rewrite this as ln of the absolute value of 3x squared minus 2x plus c. And that's your answer. Ta-da! Now, I know it seems like, nah, I mean, this one isn't as hard as the other one, but it's just because you're getting a little bit more used to doing this, right? But also I wanted to show this one just because it leads up to this next example problem right here. Let me zoom out a little bit here and put this problem right next to it. This is the next problem I wanted to share with you. Let's say I have here, instead of that, is going to be the integral of secant squared x over tangent x dx. Right? If you can look at this and you start to recognize patterns right now, can you see that this looks very similar to the problem we just did? Right? If you look and think in terms of derivatives. Tangent x is the function that's in the denominator. and it's clearly the non-derivative, I'm sorry, the derivative of tangent x is going to equal to the function up top, right? Derivative of tangent is secant squared, which is kind of like what we had here, right? So let's take a look at this problem. I'll put that problem back up in a second here, but let's take a look at this problem. Let's say I was having here, let u equal to tangent of x. That means that du is equal to secant squared x dx, which means that du over secant squared x is equal to dx. So again, I have this right here to replace my dx, and I have this right here to replace my tangent. I can rewrite this out as the integral of secant squared x over u times du over secant squared x. The secant squared x's cancel each other out. I'm left with the integral of du over u, which tells me, again, that's just going to come out to be ln of the absolute value of u plus c, which means that this is equal to ln of the absolute value of tangent x plus c. And this is what I'm trying to explain to you guys. A lot of this stuff looks crazy complicated. But they follow the same algebraic steps. They're just written with different stuff. And that's why it's kind of like, in the past, I used to have students who used to ask me, just show me all the possible combinations of these things. And can you kind of understand, like, it's impossible for me to show you all the possible combinations. All I can really do is show you like specific patterns. And they all have these specific patterns that you should be able to notice, and you should be able to find out what they are. And if you can't, and if the problem doesn't allow for that, then the person who created that problem is just being cruel. For Calc AB, right, it's the freshman level course when you go off to college, by the way. It's one of those things that kind of eases you into it. You're supposed to be looking for patterns. That's what they're training you to do. You're looking for things and ways and techniques to solve these problems. And if you can't find it, then, well, you got to try something. You can't just leave it there. But yeah, U-substitution is our first method for our first technique, I should say, for solving these things. And it's not always as clear cut. It takes a little bit of work and practice to get used to it. But yeah, you kind of just do it. Let's see here. Let me show you another one. Let's do another one. Let's do another one. Were you guys able to copy that okay? Did I go by that too fast? Are you guys all right? You guys will let me know, right, in the chat if you're still copying something. Please let me know if I need to go back. All right, let's take a look at this. Sometimes U-substitution gets a little weird. A little bit. You ready? Here we go. Let's say I was asked to integrate the integral of x times the square root of 2x minus 1 dx. Now, in this particular pattern, you might notice that one function is not the derivative of the other function. It's because it's the same power, right? If you have a problem where you have two functions that are being separated by something, and it has a particular power that's the same, it's a little bit different. We can still try U-substitution, but we got to do a little bit of trickiness with it. Okay, a little bit of trickiness with it, and you're not gonna like this. All right, that's not true. Maybe you'll love this because maybe you'll appreciate the trickiness that needs to go that needs to be involved in this problem. You ready for this? I don't know. This one's like a little bit weird, but we just try. I'm gonna go in there and I'm gonna let u equal to 2x minus 1. Let u equal to 2x minus 1, right? That means that du is equal to 2 dx, and of course, that means that du over 2 is equal to dx. So I have my substitution possibilities here. I can substitute this out with that, and I can substitute this out with that. So I have here the integral of x times the square root of u. And then over here I have du over 2. Now my issue is, right, when you look at this, right, remember I always told you, look for a way that you cancel out your x's. U-substitution it's about you, it's not about your x's, right? That's the way that I like to look at it. When you have here, you got u's and you have x, and that's just not okay. So I can't actually integrate this. So one technique, right, along with U-substitution, is you can sub out what x is equal to. So you'll say, what the heck are you talking about? Take a look at this right here. This u is equal to 2x minus 1. I could, in theory, figure out what x is equal to and substitute that out as well. So over here, I'm going to not only substitute out u and du, I'm going to do a change of variable method. That's what this is called. We're going to be changing out that x. So I'm going to go ahead and solve for x here. So when I solve for x, I end up with u plus 1 is equal to 2x. Divide both sides by 2. U plus 1 over 2 is equal to x. This right here, this is going to allow me to switch out what this x is equal to. Now, I know this seems weird, and I agree with you. It's like, why would I ever consider doing this? And I'll be honest with you, when I first saw this, I never would think to try this out. I would never have thought to try this out. So check this out. X is going to be replaced with u plus 1 over 2. The square root of u, I hope you guys are okay with that. That's the same thing as u to the 1/2 times du over 2. You ready for this? You can clean this up and simplify this. The u plus 1 over 2 and the du over 2, that's the same thing as 1 over 4. Would you guys agree? That's the same thing as 1 over 4. And then the u to the 1/2, I can distribute and multiply with this right here. Where did I get the u plus 1? So originally, it was u is equal to 2x minus 1. I added 1 to both sides. Thank you for asking that question, Monica. Yeah, so that's the thing. You could modify your U-substitution. I think that's the part that used to trip me out, is the fact that you can actually mess with this thing. You don't have to just take the derivative immediately and get the du and the dx's. You can actually modify this thing and substitute it out. Now, why would you do that? Okay, more questions. Good. Max, where did the u to the 1/2 come from? The square root function. The square root of anything is equal to anything to the 1/2. So u to square root of u is the same thing as u to the 1/2. Did that answer your question, Max? All right. Square root of x would be x to the 1/2. Yeah. Okay. So that's what I did here. So that x I replaced with this. The square root of u I rewrote like that. And then down here, right, I have this monstrosity of a looking thing. So what I'm going to do is I'm going to slowly break it down. Everything's multiplying with each other. So this thing has a half. This thing has a half. I'm going to write that down as a 1/4 in front and deal with that a little bit later. So 1/4, and then I'm going to have here u plus 1 being multiplied with u to the 1/2 power. This of all, of course, has a du at the end. Now, there's no x's involved now, right? That method at the start there, I changed out the variable and I replaced it with the u. Okay, you ready for this? This is multiplying with this. Why don't I just distribute this, right? Why don't I just distribute this? So 1/4, that is a constant. I'm going to go ahead and write that in front of the integral, because you can just do that. There's no u's with it. There's no x's with it. I'm just going to write that 1/4 in front. U to the 1/2 times u is the same thing as saying u to the first power times u to the 1/2 power. Do you guys know what you do when you have the same base? Do you guys know what you do with exponents when you multiply things with the same bases together? You add them. That's right. That's right. So this is going to become u to the 2 over 2 right there is the same thing as 1. So this is going to be u to the 3 over 2 plus u to the 1/2 du. I might have lost a couple of you. All right, you guys remember, right? X to the second. You know what? You know, if I had, for example, x to the second times x to the third, you guys will write down x to the 5th without blinking an eye. But if I have a u times u to the 1/2, it's the same concept. You're just going to add these together. 1 plus 1/2 is 1.5, or in other words, 3/2, right? Common denominator is 2 over 2. So it would be 2 over 2 plus 1 over 2. That's how I got this 3 over 2 right here. Okay? That's that in a nutshell. U to the 1/2 times 1 is just u to the 1/2. Now, here we go. This is the power rule in a nutshell. I can just integrate this now. So this is going to be 1 over 4 times, I can integrate this. This is going to be u to the 5 over 2 divided by 5 over 2 plus u to the 3 over 2, because again, the power rule, I'm adding 1 to these powers, divided by 3 over 2. Excuse me. This, of course, is all included with a plus c. I know this is a lot. We're almost there. This is the same thing as 1 over 4 times 2 over 5, u to the 5 over 2, plus 2 over 3 times u to the 3 over 2, plus c. We're almost there. Actually, I would just substitute this out right now. 1 over 4 times 2 over 5, and instead of u, way back at the beginning of the problem, u was equal to 2x minus 1. Let's go ahead and replace that out. 2x minus 1 was what u was originally equal to. And my lights are still doing this here? That's creepy. To the 5 over 2 plus 2 over 3 times 2x minus 1 to the 3 over 2 plus c. This is what I mean, though, right? Like, by the way, you could stop there. If it's a multiple choice answer, they probably finish it off and write it out like this. Distribute the 1/4 to everything here. So this 1/4 would multiply this out, and you get 2 over 20, or in other words, 1 over 10 times 2x minus 1 to the 5 over 2, plus 2 over 12 would reduce down to 1 over 6 times 2x minus 1 to the 3 over 2 plus c. And this would be the answer that's in the multiple choice one. But if you're doing free response, I'm perfectly happy with it here. But that's the thing about these U-substitute. That's the thing about these integrals. They seem weird, but that's all I can really say. I always thought they were weird. But once you kind of do them and get the hang of them, it kind of comes second nature. You know what I mean? Like, it's just an operation when you do these integrals. But now these operations require like techniques, because you can't just do the operation straightforward, because you don't have a property for like functions that are multiplying with each other, or a property where functions are dividing with each other. You kind of have to do like this secret magic technique that kind of like, it works out, but you have to go like the roundabout way. You know? It's a little strange. It's a little strange. Yeah. The technique gets a little bit weirder. I don't think we have time for... there's one I wanted to show, but I don't think it's going to be tested. So that's why I'm like kind of like hesitant to show you. But let's just do it anyways. But yeah, this is... Oh man, my notes are all over the place. This is technically like part of differential equations, because you use these techniques to help you solve differential equations. But technically, what I should have titled this is I believe is I guess I would title this as different like techniques. What techniques? Oh, let me answer this question first. Wait, so how did you get the variable c in the equation? Whoa, 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 Sam, whoa. So that's the, okay. Remember, Sam, the plus c is not just some random variable. Well, I guess it is some random variable, but it's not, it's a constant that comes from when you do a integral function, when you do the integral operation. So when you integrate a function, right? When we first learned about integrals, right? Let me put this off on the side here. When we first learned about integrals, Sam, right? Yeah, no, that's perfectly fine. So when we first learned about integrals, right, we did the integral from a to b of a function, right? And we found out that this right here taught us that if I had a function that looked like this from a to b, the integral from a to b gives us this area. That's what the integral was, right? We found out that if we integrate something, it's a summation of all these areas added up from a to b, and it gives you that area. And then further along when we learned in calculus, we found out that with the fundamental theorem of calculus, we found out that if you have a function, let's call it f of x, and I were to take the derivative of that capital F of x, it would give me this little f of x, So that means, right? Oh, that means we also then found out that if we do the integral, right, of a function dx to calculate it from a to b, we found out that all we needed to do was find this thing called the antiderivative. So we found out that the integral and a derivative are inverses of each other, right? Evaluated from a to b, which is f of b minus f of a. Now that was all well and dandy whenever you had an a and a b. We found out that those values right there, right? Now, what this ended up leading to was just the integrals in general. If I had the integral of a function f of x dx, right, that tells us then that there's a connection between this function and its antiderivative. But there's a catch. The catch is it's not enough to just tell us that this is the original function, because if you were to do this, I don't know if you realize this, right? The example that I broke down before is if I took the integral of, let's say, 2x, for example, dx, right? We know that's going to be x squared. But here's the thing, Sam. If I had a bunch of functions like x squared plus 1, x squared plus 2, x squared plus 3, x squared plus 4, would you agree that if I took the derivative of all of these functions, they all look like this? Right? The derivative of x squared plus 2, why, that's just 2x. Derivative of x squared plus 3, why, that's just 2x, right? So the way we counterbalance this is we need to find a way to incorporate all the possible pluses right here. And the way we do that is we just tack on this plus c. And that plus c stands for a constant that shows you like, hey, there's a c here that you might need to find. As for now, we're using this as a placeholder to say like it could be any of this. And that's why I call this, or not I call this, it's called, this right here is called the general solution. It's called the general solution. When we solve and find out what c is equal to, so if I find out that, oh, it's like, you know, x squared plus 2, when I actually find out what c is, if c is equal to 2 by plugging in some numbers, then we call this right here a particular solution. And that's all there is to it. That's where that plus c is coming from. And that's what makes it a differential equation, is this whole dx and the dy and all the differentials that are in there, right? That's a little bit different than derivative, which was dy dx. So that's kind of like the craziness that's connecting it all together. This also leads, I'm sorry for going off these different things here, but I just think they're kind of neat. The crazy thing is this here. Give me 1 second. Let me show you this. Hopefully that answered your question, though, Sam. I think I answered your plus c already, I think. But I kind of like, I can't get off this part. But check this out. I don't want to save that. I want to show the slope field generator real quick. So, for example, something like this, right? Right, 2x was our function, and this is their slope field for it, meaning like if I were to look at it like right here, can you kind of picture it? Right, if you can you kind of picture it like this right here is the different derivatives values of this slope field, or of this differential equation. So if I know that the derivative, right, dy dx is equal to 2, right? We have some general idea that the original function is going to be x squared plus c, right? Because if you take the derivative of x squared, we get this. And I just realized I'm out of time. It's 10:37. I'll continue this next time. Shoot, we'll have to wrap this up later. I'll go ahead and I gotta let you guys go. We'll talk about this next time. I'll start off the class with this. But yeah. Sorry about that, guys. Went a little bit over, but have a good rest of your day, guys. Stop by, please. Stop by during tutoring today if you guys want to. Other than that, have a good rest of your day. I'll be here after school. I'll be here during office hours. Bye, everybody. Dang it, ran out of time.